We will now be adding weights to a mesh using KineFX. We'll start with basic weighting. I have a very simple setup to start with. This rig is a line which has been converted into a rig using a rig doctor node. We can manipulate this using a rig pose node. The mesh that we'll be rigging is a box. Setting up weights in KineFX is reasonably straightforward, but it can be confusing as most of the nodes relate to the object-based rigging system. We can actually ignore a lot of these nodes, for example bone link, capture region, and the bone capture proximity nodes. Most of these do not apply to KineFX. There is only one real option with KineFX, and that is to use the bone capture lines node. When we connect the bone capture lines node, we'll see that the rig is subdivided. The purpose of this node is actually to add an attribute to the bones, and this is the bone capture attribute. First, we'll have the bone capture attribute for the initial bones, and this will have specific values for the bones. There are not any real weights added at this point. The line is essentially subdivided, and each point records the bone that is influencing that point. So the first points are our original points. The remaining points are the points that will be used to calculate the weights. At this point, there is no interpolation of weights for these points. Most of the parameters in the bone capture line node are actually for the object level rigging. For example, the parameters related to the bone link and the capture regions have no influence. We generally do not need to update any of the parameters on this node in order for it to work for KineFX. The next node that we're using will be the embed node. This node will have the first input set by the mesh. The second input will be set by the bone capture lines node. This node will create volumetric 3D geometry based off the mesh, and it will propagate the bone capture data throughout the mesh. This node will not calculate any of the information, but it will be important for allowing for more accurate weights. We can return to the scene view. Here we have our generated mesh. The mesh is actually a volume. The geometry has been generated within the mesh, not just on the surface. By default, the volume has been enlarged, but we do not need this in most cases. And I'll set this value to be 0. We will also turn off the enlarge input mesh option. This is how we'll use this node in most cases. There are reasons to use the enlarge offset, but we will deal with those later. If we look at the mesh, we should see that the skeleton is now part of the generated geometry. We can get an idea of the mesh density using the knife node. I'll delete the primitives beneath the plane of the node. If I move the plane, we'll see how the geometry has been generated throughout the cube. This geometry has been generated for the bone as well. We'll look at the reasons for generating this geometry after we have finished this setup. The next node we need is the bone capture biharmonic node. The bone capture biharmonic node will use the information on the tetrahedral mesh to generate weights for our main geometry. In the geometry spreadsheet, the size of the bone capture attribute will be much larger. Each column will carry the information for the influence over bone on that point. Now that we've generated the weight attributes, we can drive the mesh with the skeleton. We'll do this with the bone deform node. You can also use a joint deform node, but this is just a wrapper for the bone deform node. The first input of our bone deform node will be set with our mesh. The second should be set by the skeleton for the rig. This should be the default rest pose of the rig. The third input will be set with our animation. We should now be able to drive the mesh with our deformation. Now we can look at why we're using the approach using the tetrahedral mesh. The setup is essentially the same as the setup for the previous scene. The rig is slightly more simple and we have different geometry. I'll select the tetrahedral mesh and we'll set the viewport to wireframe. The most basic way to calculate weights will be to calculate the weights based on the proximity to the points. The problem is easy to see in a mesh like this. We want points to be weighted to the first bone, but they have a much closer proximity to the other bones. This is where the tetrahedral mesh comes into play. Instead of calculating direct proximity, we use a series of points. Instead of calculating a direct path, we'll perform a process which is closer to joining dots. Each point will calculate the weight based on the closest point in the mesh, rather than the bone itself. This way we'll actually get to the final deformation using points that have a direct path towards the bone. The end result of this approach is that we have weights which conform properly to the geometry. There are limits to what we can do using this approach, and it is important to know where and how this approach can break down. The fundamental problem is the tetrahedral mesh needs to work with solid or closed geometry. Small holes will not cause major problems, but when we have open geometry like this, the proximity of the bone to the geometry becomes very important. In this case, we get a broken result. To a certain extent, we can fix this by enlarging the tetrahedral mesh. This will usually work, but for cases like this where the bones are not part of the mesh, we will often need to check the results more closely. There is one more case which we should look at where it is beneficial to know how to approach weighting. In this example, the weighting will also fail. I've weighted the flat geometry with points that have been scattered along its surface. If we move these joints, however, they will have no influence on the mesh. This is another case where the enlarged mesh is important, and that is dealing with sections of a mesh or flat surfaces that have joints directly affecting the surface. This will be common if you, for example, have a bone-based rig for cloth, or for things like a bone-based facial rig. If the tetrahedral mesh is flat along the surface, no weights will be generated. The weight attribute will be transferred to the geometry, but all the weights will have a value of 0. So whenever we control a section of a surface with joints, we'll need to enlarge the tetrahedral mesh. That is a very basic overview of adding weights to the mesh. Next, we'll look at modifying those weights.